u of x minus st.
Yes, right. So expecting traveling wave solutions, okay. We're going to take the following onsets, which is that u of xt is equal to v of psi, or in other words, v equals x minus st. Okay. Now, a Fourier mode solution is a particular form of this, but it makes a stronger assumption about the form of v. V may not be a nice, clean exponential function. It would be if it was a linear problem, but it's not in this case. Okay, so this is our mapping, right? And so again, this takes us from t and x. Essentially, we're going to map to psi, right? Because we're assuming, just like in the case of method of characteristics, that we have some initial solution, right? And along these, psi is constant. And the wave is just going to propagate with some constant speed, okay? So traveling wave onsets makes two strong assumptions. One, that you have a shape that as long as you travel along these characteristics, it's going to hold the same shape. And also, all parts of that wave travel at the same speed, okay? So it's much more restrictive than what we did in method of characteristics. It's like doing method of characteristics, but you're already saying what the characteristic is, okay? It's this nice, constant transport characteristic, okay? All right, so that's the idea here. So if we plug this in, let's just do this carefully, right? Then we get du dt equals minus sv prime by the chain rule, right? This is minus st popping out. U is just sort of along for the ride, right? U is just v, and then uxx is equal to just v prime prime, okay? So that means that u sub t equal uxx plus u1 minus u. This is just going to become minus sv prime equals v prime prime plus v1 minus v. And now we have a second order nonlinear differential equation, okay? So to convert this to a 2D first order system, remember the trick from ordinary differential equations, you just define a new variable and you call it, you'd say w is equal to v prime, okay? So v prime is equal to w. This is your first equation. And then if I look over at this equation, if I move this to the other side, then I have an equation for v prime prime, which is just w prime, right? So w prime is equal to minus sw minus v1 minus v, okay? All right. So how do we understand these solutions in this case? It turns out that the equilibria give us some information to start with, right? So let's start out with the possibility of what are called standing wave solutions. What's a standing wave? It's a wave that stands still, okay? So this would be the particular case where S is equal to 0. Do we have any standing wave solutions to this equation? Well, if I do that, I end up with v prime equals w W prime equals minus V1 minus V. So the equilibria in this case are going to be where V prime equals 0, W equals 0, and where W prime equals 0. In other words, where V times 1 minus V equals 0, or where V equals 0 or 1. Okay, so our equilibria are going to be 0, 0, and 1, 0. Okay, their stability of our equilibria, in this case, are given by our Jacobian. Okay, what's the Jacobian of this system? Well, it's just going to be 0, 1, and then the derivative of this is going to be minus 1 plus 2v, and then 0. Okay, so the Jacobian of 0, 0 is equal to 0, 1, minus 1, 0. So you get lambda squared plus 1 equals 0, or lambda equals plus or minus I. The Jacobian at 1, 0 is going to be 0, 1, 1, 0. So you get lambda squared minus 1 equals 0, or lambda equals plus or minus 1. Okay. So what are those two fixed points? How do you classify them? You got to shake the dust off your ODE textbooks. Baseplan analysis. This is a center, right? Stuff spirals around it, but it doesn't spiral out or in. It just keeps on rotating around the fixed point. What is this? It's got one attractive direction and one repellent direction, right? The saddle. Yeah. Okay. So we have a center and a saddle again. Okay, similar to what we had last time in the KdV equation. And the circles that rotated around, these are like periodic solutions. Okay. All right. So let's look at what this looks like. V, W, here's 0, 0, here's 1, 0 here. Okay. And we have some attractive and repellent directions here. And so let's just focus on the rotations around this fixed point here, right? So here's our center. I'm going to look something like this. And so the idea is that V as a function of psi, but remember psi in this case is equal to x minus st, but s is 0, so this will just be x, right? It's just a standing wave. Everything just stays still. So you'll get just periodic solutions that look like this. Again, we named these last time. They're called canoidal waves, okay? And I want you to spot, for me, what is wrong with these in terms of the original thing that we're trying to model.
Are they going negative?
Yes. That's a problem because you can't have negative population. Okay. So these are real solutions to our PDE, but not ones that we're interested in because they're non-physical. And usually Fisher's equation is meant to represent populations or chemical concentrations. And so you want to ignore these because essentially b is less than 0. Okay, so we can't have negative rabbits, for instance. Okay. All right. So let's move on to maybe